or my session today for CodeRage 9 is about the parallel programming library using C++. And there's all my contact information. I'm the Vice President of Developer Relations and Chief Evangelist. I've had the pleasure of working with all of these developer tool products for the last 29 years, a little over 29 years. My email address, my Twitter account, and a short URL form to get to my blog on the new Community 3.0 site. The new parallel programming library is based on a history of parallel computing. In particular, some work that has been done at Intel, at Apple, at Microsoft, at MIT, and others to create a new library called system threading. It's in the system threading namespace for C++. There's a header file with the interfaces and the source code. And there are three main areas in the library that are implemented in code, not in the language. A parallel for loop, tasks, and also futures, but I'll mention a little later some of the issues in using the current release for future variables. But allows you to easily add parallel programming to your applications. You may have been using the threads interface or the operating system interfaces for threading. These libraries are knowledgeable and use some of those capabilities. And ultimately, under the covers for each language and each platform, it allows you to take advantage of these new multi-core and multi-processor technologies that we have. My MacBook Pro has 4 cores, which means has 4 cores in it. Actually, 8 cores in it. So even some of my smart devices, like smartphone, has 2 cores. So taking advantage of this world where the operating system will let you start up different tasks and will portion them out to the processor cores that it knows about. And again, it's the same implementation on each platform. So same library, same interfaces, whether you're programming for Win32, Win64, Mac OS X, iOS, and Android. And the operating system knows about how to schedule for the different cores that it finds so that you don't have to think about that in a sense. But the parallel programming library uses threading that is aware of what's going on in the CPU and does a lot of self-tuning for you. There is a thread pool, the global thread pool, but you can also create your own thread pools if you choose to. The thread pool can, as I mentioned, tune itself based on what's happening. And again, you can create your own thread pools and pass those as parameters if you want to change what's going on for the benefit of your programs, your algorithms. And I'm not going to go deep into the underpinnings of the architecture because Alan Bauer has a session tomorrow. He's the architect of PPL, and he will go in much more detail about the implementation and what's going on down at the operating system and hardware level. So as I mentioned, a for loop has an iterator that allows you to do the processing inside of the for loop, especially handling the index that you're processing through on the for loop. It has a break parameter so that you can break one of the iterations of the for loop, break out, and then you can also do more control of the parallel for loop to see where you are on the iterations. there's a task, a T-task class, that allows you to start one or more tasks and wait for completion of all of the tasks or any of the tasks. Futures are still being worked on for C++. They're implemented for Object Pascal, and the team is working on a few issues to add future support. So we're going to skip future support for now in C++, but you have full support for the parallel for loop and for tasks. Now the for loop accepts, on the Object Pascal side, anonymous methods. For C++, we create an iterator event function and pass that as part of the for loop call to do the incrementing for us and the processing. Bruno Babet is doing a session tomorrow consuming Object Pascal code in your C++ applications, and he's going to talk about an approach for using C++ lambdas as part of the parallel for loop call. And again, tasks have wait for any and wait for all. And just a note, inside of a task, don't do anything that might depend on the main application thread, because your task might complete, but if you have some user interface elements like a label or something in your app that you want to update, you'll want to do that in the main thread. I had an example I was working on where I moved it from the for loop into a task. The task completed, but the last statement was a thread synchronized, so the task waited even though it quote-unquote completed. And then in the main thread, it was waiting for all of the tasks to complete, and they were just sitting there in a deadlock. So again, in for loops, fine. You'll see an example. For tasks, if you're doing a wait for all or wait for any, you'll want to do any synchronization or UI update outside of the tasks themselves. Okay? All right. Enough slideware. Let's switch over to the IDE and look at some samples. So there's one sample that ships with C++ Builder exe7, and that's Conway's life simulation that dates back to Scientific American 30 years ago or so. And it's a parallel implementation of that. But let's start simply and look at a simple example. This is a C++ example. It has a button and it has a label. And the code behind just says, let's initialize the label with something, the dash dash. And then we're going to use the T-task and call the run method. We're going to pass a proc interface to do the processing for us. Now this TCP task is going to take the variable, which is defined over in my class. It's just an int. And then the label is the label in the UI. So we want to be able to update this label inside of the task. And since I'm doing a task run and not caring about waiting for other tasks to process, I can update the user interface. So in the CPP task, I have my invoke of the method, invoke method, where I'm going to say sleep for some number of milliseconds, just 3 seconds. Generate a random number into that value. And then I'm going to do a thread synchronize to update based on the value to update the label. So that event, which is a thread proc event, which is done up here, where in the invoke of that method, I'm just going to set the text property of the label. This is a multi-device app, to the string of that, whatever that value is. So mapping the value passed in and the address of the label of my UI. All right. So pretty simple. There are lots of other options on the run. If I go up here and say task run, and then we can pass it the function. We can also pass an optional thread pool if you want to have your own thread control. And also you can have a notify event. In this case, I'm using proc. But you have those 4 options. And also at the top of this FireMonkey app, I have a scroll bar with a float animation. And I want to show that while the task is running, that the user interface is still reactive. So the float animation is parented to the scroll bar. Auto reverse is true, enabled is true, loop is true. The duration is 1 second at a time to do the animation. We're going from value 0 to 100 and back because it's reverse and loop. And the property that we're changing is the value property of the scroll bar. So the scroll bar value starts at 0, and then the float animator is going to every second update that. And we'll be able to watch the scroll bar move back and forth. So let's run the app. There's the scroll bar, and again, it's responsive that way. Let's call the task and use its run, and notice that the interface is still active, and eventually the label is updated with that random number, right? Okay. So just a first quick example of using the parallel library in C++, in this case using a very simple task and running that application. Let's look at another task example. This one has 2 buttons. The first button will set the caption of the label, set the value to 0, and then I'm going to use a task create method. Let's look at the options for task create just real quick. Okay, we can pass it an event to be notified for the task, or again, we can pass it a proc and also thread pool. Then after we create the task that points to this task value, and it has 3 parameters. In this case, one is that variable, one is a number of seconds to sleep, and then the user interface that we want to update. And so it will sleep that sleep value and generate a random number for L value. And then we'll call that task start. And let's look at some of the other options that are available once we have a task created. We can wait, we can cancel the task, check to see if it was canceled, get the status of the task, execute it, and so on. So we'll start it and then output the value. And in the second button click, we'll create an array of task interfaces, iTask, and we'll create the first task, telling it to sleep for 3 seconds, create and start it, create the second task, tell it to sleep for 5 seconds, and then we'll call wait for all tasks to complete, passing it the array of task interfaces, and then the number of tasks that we have using size of the task array and the size of one element minus one. And then we'll just put up a show message when we're all done. And again, we've mapped our parameters, and they're used inside the method for invoking that CPP task, and then synchronizing the output of the label if we want to do it. In this case, I put a note, and I'll give you all the source code for these examples. We don't want to do a thread synchronize inside of a task. We could always use tinterlock to use the synchronization object that's been around for a long time and do some kind of addition or replacement of a value. Okay, so let's run this example. And the first one is delay message. That's fine. It just started a task, had it run, and completed it. And then we'll click wait for all, and it will start the two tasks, and eventually both will complete, and we got the message box. We can debug the task process. So let's go up to our interface, and let's say run with debug. Let's go and do the one task, and here we are, and the sleep value is 3,000, and then we can continue, and it works. We do wait for all. Here's the first task create, and then as we step or run from there, we'll get, notice it went through the statements. That's the first invocation, sleep value is 3,000, and let's run again. Here's the second invocation, 5,000. And then when we're done, we'll eventually get back the message box that we're all done. So the creation and start just runs, and we can debug our multi-task application. All right? Okay. Third example is a parallel for. It's got two buttons. This is a FireMonkey app. The first one is simply going to is the serial version of finding prime numbers. So isPrime is a function that runs through all the numbers from 1 to 50,000, looking for prime numbers and counting the number of primes. So it says, let's go from 1 to whatever the maximum is. If that number is a prime number, increment the total of primes found, and then output the time it takes and the number of primes found. It's using the stopwatch, the tStopwatch class in the system diagnostics namespace unit, and to get an accurate millisecond count. The second button event handler is the same idea. It starts the stopwatch. In this case, it uses the tParallel for. I don't have an owner. We'll go from 1 to the max. And then for C++, I need to pass a method And the method is going to do the processing for me. And it's going to be past the iteration of each of the values from 1 to max for the for. And then we'll stop the stopwatch and output the time and the total found. So what is this iterator event? It's void fast call. It has a sender, the application that called it, and it's past the index. That's one of the options. So inside of the code, I say if is prime, the index I'm passed, from some value from 1 to the maximum. And if it is prime, then I'm going to use tinterlocked from the system synchronous objects, sync objects, and I'm going to increment that variable TOT, which again is defined over here in the public section of my form class. And again, stay tuned to Bruno's session, where he's going to show you how to use lambdas. All right, let's run this example. And so there's the sequential for loop. Took 362 milliseconds, and it found 5,134 primes. The parallel for runs in about a third of the time, 113 milliseconds, and again found the number of primes. All right, if we set a breakpoint inside of the iterator event and run with debugging, do the parallel for. Here's the index is 1. Let's run again. 2. And so on. So under the covers, the parallel programming library is going to create a bunch of threads. The operating system is going to portion them out to as many processor cores that are available. In my case, on my MacBook Pro, I'm running Parallels Desktop 10, and I've given it, let's see where the configuration is. Let's go here. I've told it on the CPU to use 4 CPUs. And so if it runs so fast that I can't really show you the task manager with the processor cores running. Just because well, notice the time took longer because I was debugging it. That's the stopwatch. We can go back again and get the faster time. So if you have a longer running application, then you can actually bring up the processor cores and watch them all being used. All right. And while I'm in here, let's take a look at some of the options for the parallel for. And it's a big long list of overloaded function calls. The most one you'll use is, again, the low inclusive, high inclusive, and the iterator event. You could specify a stride, which is the number of iterations that'll take place in a chunk. You could also pass a thread pool again down here as an option. You can also look at and control the loop state to see what's happening. So many different options on the parallel for. And again, all of the parallel programming library works for all the target application types for all of the platforms that we support. So, as I mentioned, Win32, Win64, OS X, iOS, and Android. VCL apps, FireMonkey apps, console applications, server applications, whatever the target types are and the target platforms, the parallel programming library works for you. Okay, one last demonstration. And this is an example that ships with XE7. Actually, it comes in two forms. Let's go to our samples, C++, which are in public, user, public documents, Embarcadero Studio 15, samples, C++. In the RTL folder, there's a folder called Parallel Library. And in the Parallel Library, there's a VCL version of the project and a FireMonkey version of the project. And then shared code, which includes the header file and the life engine written in C++, the underlying engine. So let's go and look at that shared code. And this implements the life engine, the different threads, updating generations. And if we go down a little bit, you'll find a parallel for loop. And in the life engine, he's got an iterator event that takes who the sender is and the index of the generations. And then it calls process cells for that index. So for serial support, it'll process one generation at a time. For the parallel version, it will process lots of cells of the grid. And we've got a checkbox here for running it serial or parallel. So if the life engine is not null, then we're going to set the life engine to parallel, set that true. And then in the code, of our application, when we click the start button, we can start and stop. We can see if it's running. And then if parallel is set, we'll run the parallel version or the serial version. So again, on execute, we'll check to see if it's parallel. Then we'll use the parallel for. We'll take the original board bounds, low and high, and then we'll have this iterator event that will go through and process the cells. So let's run this example. So let's just start it. And you'll see the generations per second. And we can kind of scroll through the interface and look for things that are happening. Let's stop it. Let's load a sample life file. And there's a bunch of these different starting points for the simulation. And again, we can scroll around and see what might be happening. And let's stop it. Let's turn on parallel. We got 8 generations per second. And now notice in the parallel version, we've got lots of cores running. So let's go in this case and bring up the task manager and look at the CPU performance, and notice that all 4 cores, I told my VM to use 2 of the CPUs, the 4 CPUs in this MacBook Pro. So it's fully utilizing all 4 of the cores that this VM has in running the simulation. Okay. And let's stop and recenter and start it again. So that's, if you've never seen the life simulation before by Conray, it looks around life civilizations, and there's interactions that take place. Here's a walker, some things happening. Here's in a sense, the civilization sort of interacting until they become stable. You'll see some stable communities, in a sense. All right. Main thing in here is not that, although that's pretty cool, is to see the impact of the parallel for loop versus the running it serial. All right. And again, the source code for Conway's life simulation is there in C++ in the samples. If you don't have XZ7, you can download the trial, the 30-day free trial, and you'll get the samples as well, so you can check it out, play with it. You don't get the RTL source code in the trial, but you do get the samples that you can explore. And I'll put these other samples up on my blog sometime this week or early next week with some additional examples that we're playing around with here. Okay. 2 sessions I sort of mentioned along the way that you should be sure to watch. They're both tomorrow. They're late in the day, but we'll have the replays, and we might have some other times where we might rerun those. The first one is the Parallel Programming Library Architecture with Alan Bauer, Chief Scientist. That's at 5 p.m. tomorrow. And again, that's going to cover not only an introduction to parallel programming, but the implementation that Alan did across all the platforms in the library. And then for some of this interaction between Object Pascal code and C++, the Parallel Programming Library is implemented in Object Pascal. Bruno Babet is doing a session tomorrow at 6 p.m. about tips and tricks for C++ programming when you're using some Object Pascal code, which VCL, FireMonkey, and some of the other parts are implemented in Object Pascal. And he's going to talk about how you could use lambdas in C++, just as an Object Pascal developer would use anonymous methods, and other cool C++ tips and tricks. Bruno works on the C++ compiler in R&D. The Conway's Game of Life is Paralyzed. That's in the Rad Studio SourceForge repository, and it's shipped with the product. So you can go out to SourceForge, just search Rad Studio, SourceForge, demos. You'll get to that SourceForge area. Go to the branch, Rad Studio XZ7 CPP, and you can find the parallel library Conway's Life example. Stephen Ball has done some blog posts, and I've blogged about this on my blog already. Those are Object Pascal, but you'll see the functionality and different samples on his blog. And with that, let's switch over to the Q&A log. Let's see. Okay. Let's see. Rob was asking, it's a long one. He's doing drag and drop. Will the parallel library help with that? Not specifically, although, again, as you saw with the scroll bar, if there's sort of animation or additional operations that seem to get blocked for some reason, using the parallel library to do some of your programming in your main application would free up other things to happen in your user interface. let's see. Rob's asking, there are other kind of either messaging libraries or other parallel computing libraries like OpenML and so on. He's zero message queuing, 0MQ, nano message. Is there anything plans to support messaging system for communicating between computers? There's no current plans, but there's lots of things the team is looking at for parallel in the future. I'll leave that question, Rob, for Alan's session, and I'll make sure to re-ask it again because he has a bunch of plans for the future generations of parallel library. Right now it's on the computer and platform you're building for, but there isn't any reason why it couldn't be a distributed parallel application across multiple computers. And Timur, yes, the replays will be available, and you'll get an email in the next couple weeks with the link to all of the sessions and the Q&As for them. Let's see. Can you execute the same code in Visual Studio? No, this is specific to Delphi, C++ Builder, and RAD Studio. So D is asking, can T-Task usable in your own threads or the main thread? It's your choice. You can use T-Task in your own threads. You can create your own thread pool. And you can call it from the main thread. So it's your choice how you want to do it. By default, the parallel programming library is going to use the global main thread for your application by default. But you can create your own thread pool and pass that as a parameter, as I showed you when I popped up the T-Task options and also the Parallel 4 options. You can pass your own thread pool and then manage that thread pool and go from there. And Danny, who did the Delphi Object Pascal version of this talk, is just saying that note that you can synchronize inside of a task as long as you don't use wait for all in the main thread. And you're absolutely right. That's what I was mentioning. And that first example that creates a single task isn't doing a wait for all. So I could use thread synchronize in the simple integer example. It's only when you're waiting, and we were playing with that yesterday, you could create some other mechanism on your own, but there's no way for the parallel for loop or the task system to know. It's up to you in your logic what you're using in your application. So just be careful, and in the source code you'll see a comment, beware if you are doing a wait for all that you should worry about possible deadlock. So D is saying he saw mostly static calls, but it's all dynamically usable. You saw me create a new task in the case of creating multiple tasks, but you can absolutely create any number of tasks in your application, statically or dynamically. There's no limitation in that respect on the library. It's using the power of the language, either C++ or Object Pascal. Okay, if there are any other questions, just put them in the Q&A log. Let's see. If not, I'll switch back over to, let's see. I'm not sure, D, is the number of cores definable? If you're talking about Stride, CPU cores. There's nothing at the CPU level specifically, although on certain platforms you have the ability to choose and control. Like on Windows, for example, there's some lower level APIs on Windows. There's nothing in the library itself at that CPU level, but you can specify the thread pool, and you can specify the stride of the operations that take place. And that helps control how many cores and how they're used. Alan will go more into that in detail in his architecture session tomorrow. So if you can't make it at that time, watch the replay with Alan's conversation, and he will go into much more detail about what you can do at the lower levels using the interfaces of the library.